Welcome back. We're at lecture 55. As I told you yesterday when we ended, to go ahead and take a look at the partial fractions problems. And I know you had another deadline last night, so that may or may not have happened. But if you did look at the partial fractions problems on the 5.7 WebAssign, and if you have any questions, let's start with that. And if not, then we'll go on into another topic in 5.7 called trigonometric integrals. Sounds bad, doesn't it? It's not. Well, I can't say it's not bad because occasionally they get bad. But most of the time it's not so bad. Any partial fractions decomposition issues from WebAssign or anything that wasn't clear from the lecture? All right, so let me just kind of write down the parts of 5.7 that there are and the parts that you'll be responsible for Monday's test. So the partial fractions part we are now done with. Still fair game to ask questions if and when you encounter issues with that WebAssign. But that will be on the test. Also, that was Appendix G. Had some of the background work for decomposing things into partial fractions. The integral calculus stuff is here. The background stuff is in the Appendix G. We're going to do trigonometric integrals. Today, and we need to do it a little bit tomorrow, but tomorrow's mostly for review for the test. So that will be on the test. Now the part that is in this section that we will eventually cover after test 4, but it will not be on the test, is trig substitution. And the odd thing about trig substitution, when you look at the problem, there is no trig in the problem. It's numbers and letters, but to get it to a place where we can integrate it, we have to sub some trig into the problem to make it work. So this is not on Monday's test, this particular part. Now I know this goes out to cable TV, and it's also going out subsequent semesters on DVD. This is not necessarily the case with the DVD course. Just pay attention to the pacing guide that's provided. But for you guys in this classroom, the top 2 items will be on Monday's test. Even though the third topic is in this section, it will not be included.
Will our final be cumulative?
It will be cumulative, yes. And we can talk more about that, but my philosophy on a final exam was probably motivated by my philosophy when I was a student of what final exams should be. You used to burn me up when teachers would have on a final exam some items that when you went through it the first time, they weren't even important enough to make it to the test. And then all of a sudden they have this newfound importance on the final exam. I thought that was stupid. Not that I ever called them that to their face, but I thought that decision to have those items on the final exam that weren't even important enough to be on the test, I just thought that was not wise, and made a decision that when I was in charge of making up the final exam, that wasn't going to happen. So the important things to look over are the things that made it to your test. Those were important enough to make it to the test. They must have been important. And then the only other things are things that we covered after test 4. They never had a chance to make it to a test, so I'll try to let you know when we're done with those things. For example, trig substitution is probably going to be one of those things. But other than that, your best study guide becomes the 4 tests. Okay. Not that it's going to be the same problem, but the same type of problem. Okay. So on this test, there will be a partial fractions problem. So that means that on the exam, there is a likelihood of there being a partial fractions problem. So I hope you think that's fair. It is cumulative, and there's a lot of stuff in this course. But also keep in mind that of the 2 courses, 141 and 241, this is the tamer of the 2. So if you think this is a lot of stuff, wait till you begin to sit down and prepare yourself for the 241 exam. It's quite a bit of stuff. This is better connected, I guess, is what makes this a little easier than the stuff in 241. All right, trigonometric integrals. So we are going to have a variety of different kinds of integrals. They have trig in them. We'll make some substitutions, some of which are easy, some of which you probably don't recall, but we'll refresh your memory today and try to get them in a form where we can integrate them. We'll spend some more time, obviously, on preparing for the final exam. So a trig integral would look something like this. And it's hard to say you're going to do this all the time because there's a lot of differences in what you're going to encounter in the integral itself. But it's going to have sines and cosines, and on a rare occasion, secants and tangents in the integrand, and it's our job to make a substitution, change the form of it somehow so that we can integrate it. So the key indicator here is that the power to which the sine is raised is odd. So when it's odd, and there's only one of them, sine to the 5th, cosine to the 7th, then we can take one of those and set it aside, kind of put it out here by itself, with the goal of this sine that we took out here, leaving a sine squared. The goal is for that eventually to be all of or part of du. So that's going to be the du once we make the substitution, hopefully. If we let u equal sine, which is all we have, then there's no way sine is going to be du. So we've got to somehow change sine squared into something else.
1 minus cosine squared.
There we go. So we'll take this even power. If it's odd to start with and we take one of them and set it aside, that leaves an even power of sine or cosine. And then we can somehow convert that into the other function. In this case, this is sine squared. We can convert it to something involving cosine squared. So this integral problem now becomes two integral problems because it's one integrated with this little stuff at the end. So 1 times sine is sine. And then we've got this minus cosine squared also with a sine. Although? Where'd that come from? Is that okay? Are each of those able to be integrated by fairly straightforward means? How about the first one? What's the integral of the sine of x? Okay, we're thinking of something that has sine of x for its derivative. That would be negative cosine of x, right? For this one. So that's able to be integrated. Let's try to do the substitution in our head. If we let u equal cosine, we're going to have u squared. Is the derivative of cosine sine?
Yeah.
Not exactly, but correctably, right?
Yeah.
So if we do that substitution in our head, I'll write it down in a second too, but I'm kind of wanting you and asking you to do some more of these simple ones in your head. We put a -1 here and change that sign to plus. Then we're in business. This would be du, and this would be u squared, right?
Why don't we just make u sine instead of cosine?
Where in the process?
You
Here?
know how we made u cosine?
Here?
Yeah. Why don't we just make u sine because the derivative of sine is cosine?
Because you got a square.
Because we've got a cosine squared. And if we let u equal sine, this would be u, and du would be cosine. We don't have a cosine. We have a cosine squared. So we'd have an extra cosine that we wouldn't be able to accommodate. So I guess the main reason is what Eric said. That's a cosine squared, not just a cosine. So we're letting u equal cosine. du is negative 1 times sine. So I don't think that, at least based on the looks that I just saw on your faces, that me asking you to kind of think through the substitution was something that you're battling too much. So this then becomes u squared du. What's the integral of u squared du? U cubed over 3. So it's u cubed over 3, and then we replace what? Cosine of x for u. It's an indefinite integral. We'll put a plus c at the end. How was that? Fairly tame? Not too bad. And that will be our procedure when we have a sine or a cosine to an odd power. So let's see how that would differ. Let's look at a cosine to an odd power, and let's up the power a little bit. So we'll look at a cosine to the 5th and see how that would differ from this. Anything before we move it? And then we'll also look at some that have sines and cosines both in the same integral. We kind of did that right here, but some of them take on a little different look than that. So let's say we have cosine this time, still to an odd power. And I know your question that you're thinking is a logical question. What if it's not odd? We'll get to that. That's kind of the worst case, is when it's not odd. So if we're doing the same kind of thing with this, what would be our first step? Cosine to the 4th. Take one of those cosines. And the intent is for that stuff that we moved out there to the right, eventually that's going to be du. So if that's going to be du, what are the u's going to have to be so that their derivative is cosine? They're going to have to be sines, right? So here's how it differs. It makes it a little more complicated, but not that much different. Cosine to the 4th is cosine squared squared, right? We can make a substitution for sine squared. We can make a like substitution or similar substitution for cosine squared. So if you have any other higher even power, it's cosine squared squared or cosine squared cubed or whatever the case may be. In this case, cosine to the 4th is cosine squared squared. And for cosine squared, we can replace inside the brackets here with what? 1 minus sine squared. So very similar procedure, very similar substitution. The only difference now that makes it slightly more difficult is we've got to square that 1 minus sine squared squared. So that's a trinomial. 1 minus 2 sine squared plus sine what? Sine to the 4th. And let's do one more step, and I think you'll agree that it's very similar from that point. We've got 3 terms, each of which get distributed cosine of x dx to them. So the first term is 1 times that. The next term, I'm going to put the minus 2 out in front. Got sine squared times cosine. And the last term is sine to the 4th times cosine. First one, no substitutions at all are necessary, right? What has cosine for its derivative? Sine. What do you do here? Let u equal sine of x. Derivative of u is cosine of x. So this is really what? U squared du? Exactly. Same thing here. Let u equal sine of x. Du is cosine of x. So this is really u to the 4th du. Everybody feel confident from that point? Very similar to what we did on the first example. So that's if we have a sine or a cosine to an odd power. Take one of them, set it aside. You'll be left with an even power of sine or cosine. Change it to some even power of sine squared or cosine squared, so we can make that substitution, either 1 minus sine squared or 1 minus cosine squared. All right, let's take a look at what happens when we have them both in the integrand. And let's start off with, let's say, sine cubed and cosine, I don't know. Let's just start with them both being odd. You don't need me most of the time in here. Now and then I might come in and settle some little discrepancy in here. But tell me what you think might work because of what we've done already.
Sine squared times sine. And then...
Okay, let's try that. Sine squared, I'm going to take the sine, throw it out there to the right.
And then cosine to the fourth.
I'm going to go ahead and say that. I'll take your first thing and then we'll stop. Does that have a chance of working? So when we throw something out there to the right, we're hoping that that's going to be du, right? If that's going to be du, what are the u things going to have to be? Cosines, right? Well, this one already is a cosine. So it doesn't matter if we separated that or split it up. It's already cosine. We're going to leave that alone. What about this guy right here?
1 minus cosine.
And there we go. So if you have them both to an odd power, then you take either one of them, it doesn't matter which one, and break it up and send one of those out to the right, which leaves some even power there. And for the even power, you make the substitution. For the other one, we want cosines anyway, so cosines are okay. So kind of our check as to whether this is going to work is everything in this area either numbers or cosines. Yes, because we're going to let u eventually equal cosine, and we want this stuff out here to the right to be du. Derivative of cosine is what? Negative sine. So we can multiply by -1 inside and outside, and now we're in business. So you would distribute the cosine to the fifth to this one, cosine to the fifth to this one, and then every term that we integrate is going to have a sine of x dx and a -1. It's not that, there's not that much to this one. Let's set it up. I'll just leave that out in front. You can negate every term of your answer when you're done. So cosine to the fifth times 1 times sine. Can you integrate that? That's what? I'm sorry, we've also got a -1 here, right? This guy right here. So this is u to the fifth, and this is du, right? U to the 6th over 6. Okay, the other term is cosine to the fifth times cosine squared. That's got a minus in front of it. Cosine to the 7th of x. It's got a sine of x. It's got a dx, and it's also got that -1. So this becomes u to the 5th du to integrate, and this becomes u to the 7th du. That's what we have to integrate. Is that okay? So if they're both odd, it doesn't matter which one you work with. Take one of them. We took sine cubed, and we made it sine squared times sine, and we left the other one alone. So we're going to have u to the 6th over 6 and u to the 8th over 8, and then we'll plug in every time we see a u, we'll plug in what you represented temporarily, which was cosine of x. Okay, we've got lots of examples to get to, so that's probably why I'm not going each problem all the way down to a solution. Get it to the point where I think you'll feel comfortable, and then we can go to another one. So that was if both of them had odd powers. Let's just make up a problem where one of them is odd, and one of them is even. Will the same procedure work? Looks like it's going to work, because we didn't do anything with that cosine to the fifth anyway, did we? We just kept it cosine, and we just distributed it through. So if we take the sine cubed, make that sine squared times sine, send the single sine out there to the right, leave cosine to the fourth alone. If this is going to be du, if the sine is going to be du, we want u to be cosine. So how do we make all this stuff that occupies the first part of the integrand, how do we make it cosines? That's already cosine, so we'll leave it alone. So in general, somebody generalized, if you have an odd and an even power of sine and cosine in the integrand, what will the start of the problem be? You don't have much of a choice here. Take the odd one, keep the even part here, and send that single one out there to the right as hoping that it can be du. So in the other problem, you had a choice. It doesn't matter. They were both odd. Here, there's only one of them that's odd. That's the one you actually separate. So this ends up being what? For sine squared, 1 minus cosine squared. Cosine to the fourth. I think we need a negative 1 again, right? So we're going to have cosine to the fourth and minus cosine to the sixth. And I think those both integrate now. Here's our u to the fourth. There's du. There's u to the sixth. There's du again. So I think we're to the point now where we're stuck with evens. Okay, we've got all the different ways you could have odd powers of sine and cosine. Now what if they're both even? So let's start with just probably the simplest case. Suppose we have a sine squared or a cosine squared. It's not going to help us to take one of those, set it aside, right? Because then we'd have a sine left, and we'd somehow have to change that sine into a cosine, and we're not going to be able to do that. Or here we'd have a cosine by itself. We'd have to somehow change that cosine into the other function, sine. We're not going to be able to do that. So you're not going to like this. This is what I told you is not the easy part of this. So before we try to attack this, let's review something. And this is probably in one of those cardstock pages, either in the front or the back of your book. It doesn't look like it's in the back. Looks like it's probably going to be in the front. The cosine of the sum of two angles. So somewhere in the front of your book on that thicker page, if this is not going to ring a bell, you might want to review that to see where this came from. Does anybody remember? The cosine of the sum of two angles. Or it's okay to look at that cardstock page and pick it off of that page too. Okay, so cosine A, cosine B, minus sine A, sine b. That look at all familiar? Okay, it's probably not, I mean, we don't use it a lot, so it's probably not like right there on the tip of your tongue, but it's ought to look. Let's suppose that A and B are the same. So I'll just change the B to an A. So we've got the cosine of A plus A. So wherever I see a B, I'll replace it with an A. So let's rewrite what we have in that statement, where I replaced B with A. So A plus A is really what? 2A. So this was a sum and difference formula. Now it is becoming a double angle formula. Cosine A times cosine A, cosine squared A, sine A times sine A, sine squared of A. So there's the cosine double angle identity. And we're not going to see A's in there. We'll just convert it to X's or whatever we have, thetas. But this is probably not the version that we want to actually use, because it's got both of them in there. It's got cosine squared and sine squared. So there are, although this is true, this is a cosine double angle identity, there are two others that are used more often than this one. So how could we come up with a version of the cosine double angle identity that either didn't have cosines in it or didn't have sines in it? Substitute. For cosine squared, let's replace it with so this one looks like what? 1 minus 2 sine squared. We got 1 minus a sine squared minus another sine squared, so 1 minus 2 sine squared. So we'll want to use that in a couple of moments. Okay, now let's take this and leave cosine squared alone. And what can we do with sine squared? 1 minus cosine squared. So that's exactly right. So we've got minus a minus cosine, which is really plus. So cosine squared plus itself. And then we've got this minus 1. So here's the other one that we're going to use. So we're going to use two versions. They are 100% equivalent, but one has sine squared in it, the other has cosine squared. That's where we're headed. We're going to try to do something to get rid of sine squared. This one's going to help us. We're going to try to do something to get rid of cosine squared. This one's going to help us. All right, so let's take these two formulas. So cosine 2a equals 1 minus 2 sine squared of a. And let's solve for sine squared of a. So what's the first thing we need to do? We need to get this term that has sine squared isolated. So the only other term is 1, so let's subtract 1 from both sides. What's the next thing we need to do to solve for sine squared? Divide by negative 2. So sine squared of a, or x, or whatever the letter happens to be, if we divide by a negative, doesn't that change the signs of the numerator, right? So the cosine of 2a is divided by negative 2, so it's really negative. Minus 1 is divided by negative 2, so it's really positive. So I'm going to factor out the division by 2 and then kind of distribute the negative through there. So if I do that, what do I get? 1 minus cosine of 2a. So maybe you remember that, or you use it enough to, it looks familiar. but this is one that you probably ought to recommit to memory, that particular version of sine squared of A. Now the other one was cosine of 2A equals 2 cosine squared minus 1. You notice the difference in the angles? This is twice A, and this is A. So they're not the same. So that's part of, you could think of this as a double angle identity, or you could think of it as a half angle identity, because this angle is half of this angle. So it kind of serves both purposes. This one we want to solve for cosine squared of A.
Isn't it supposed to be sine squared?
Which one?
Oh.
Yeah, it is. We use the cosine double angle identity for both of them. But you're, I think, thinking ahead to the next one. So what? Add 1 to both sides? Divide both sides by 2. So cosine squared of A is 1/2 1 plus cosine. Now there's probably the only saving grace in this whole process is these two things are pretty darn close to one another. So there's the sine squared of A. It's got a half out in front, just like this one does. This has got a 1 here, just like this one does. This has got a cosine of 2A, just like this one. So the only thing that's different is the SIGN inside of parentheses. So we're going to use that, and we're going to use that. That's a long way of getting there, but I didn't want to come up with this mystery formula that just all of a sudden pops out of nowhere. So back to the problems that we had, and we're going to use these two identities on those problems. So we had, what, sine squared? So even though it's worse, we're all acknowledging that it's worse than the other process, we do have something that's going to take this and at least make it integrable. For sine squared, we can replace that with what? 1 minus cosine of 2x. And that's, I mean, that seems like a small point, but if this angle has to be half of the angle we're actually putting in here. Otherwise, it's not a legitimate identity. So that's the worst part. Everything else should be integrable from this point. So if you want to bring the half out in front of everything, that's fine. We're going to integrate 1 with respect to x. And we're going to integrate cosine of 2x with respect to x. So I want to fully participate in this class, so I'm going to do half of these. So I'll integrate 1 with respect to x, and I'll get x. Okay? So now the other one is your responsibility. Aren't I generous today? What little subtle substitution needs to be made? We've got the cosine of something. We need a 2, right? Because our u is really 2x. The derivative of u is 2 dx, so we need a 2. And another 1/2. And now that that's there, that is cosine of u du. What's the integral of cosine of u du?
Positive.
Sine, right? We're anti-differentiating cosine, so we're back to sine. So this is sine of u, and what is u? 2x. So we are making this substitution. Sorry. Let u equal 2x, du equals 2 dx. So our integrand became cosine of u, and once we put the 2 in there, it became cosine of u du with this little 1/2 out in front. And that became sine of u, and our u value was 2x. plus c. Does that work? So the substitution is the worst part, and probably it's going to require a memorized formula. This is supposed to be even powers of sine and cosine. So let's set up another problem. Even power of cosine. It's not directly the substitution, but we'll have to convert this to cosine squared of x. That's what we're going to make a substitution for. And then we're going to square that result, because we don't just have cosine squared, we have cosine squared squared. So what's the substitution? Either call it a double angle identity or a half angle identity, whichever. It's both, kind of. That we want to put in for cosine squared.
1/2 times 1 plus cosine.
1
2x.
plus
Yeah.
cosine 2x. There's the substitution. We want to square that. So when we square the 1/2, which we have to square that too, that's a 1/4. I'm going to go ahead and put that out in front. And then we'll just square the stuff that's in the parentheses. First term squared is 1. Middle term is twice their product. That actually helps the cause, right? With the 2. And the last term squared, cosine squared of 2x. So I didn't hear anybody like scream out loud when I wrote down cosine squared of 2x. So now let's integrate each of these three pieces. 1 with respect to x. That is easy. 2 cosine 2x with respect to x. That's pretty easy. And here's the unfortunate part. Cosine squared of 2x dx. Everybody feel, we're not going to do it. Everybody feel comfortable with that?
Mm-hmm.
Everybody feel reasonably comfortable with that?
Mm-hmm.
Why is that kind of bad?
You have to go through it again.
We have to do that same thing again, because what are we stuck with? We're
Square.
stuck with an even power of cosine, right? So for cosine squared of 2x, what is the substitution that needs to be made? 1 plus cosine of 4x. Because don't we need to double that angle? Right? When we use this identity, whatever angle is in the original integrand, here we had x, and that became a 2x, right? Here we have 2x, so that becomes a 4x. Each time you use this identity, the new angle is twice what it was originally. So I'm just going to rewrite this stuff. We've all agreed that this is pretty easily integrable. Here we've got what?
1/2.
Just put the 1/2 out in front. 1 dx, right? And what? Cosine 4x dx. How do we integrate cosine of 4x dx?
U for 4x.
Let u equal 4x, du would be 4.
1/4.
Right. So we need a 4. Good. And a 1/4 out in front. Now everything is integrable, right? So the bad thing about when you square this substitution, this double angle substitution for cosine, it's going to leave you another even power of cosine. So we have to use that again, right here. Or you get to use it again. Okay, it's just fun. It's so fun the first time. We want to do it the second time. you guys know I kind of have a somewhat bizarre mind anyway. I watch a lot of sports, and I see a lot of sports stars, professional athletes, college athletes. This is a part of sports, and this has some math applications. I'll get back to how it applies to math. So you see a defensive back come up and cover his territory of the field, and he makes a tackle. And they start thumping their chest, and doing all this kind of dances. Isn't that what they're supposed to do? Isn't that what you're supposed to do as a defensive back? Or you see a running back run through the line, and he goes through the hole that the lineman opened for him and runs over a linebacker. That's neat. But I mean, he runs and scores a touchdown and starts acting all freaky and stuff. I mean, isn't that what you're supposed to do? I mean, pro players, don't they get paid to do that? Why are they getting all excited about it? I mean, that's your job. So let me relate this to this problem. So we get done with this problem. I mean, why are we not all in this room thumping our chests, and going, yeah, that's what I'm talking about. What? I mean, what's the big deal? I mean,
Because we've been videotaped for educational purposes.
Yeah, that's true. We do have to kind of behave a little bit. But I mean, I've always wondered that. Just settle down. That's your job. You get paid for that. What if somebody comes to your house and somebody's having trouble breathing and they resuscitate them? What if they go, start thumping their chest and, yeah, I saved them. I saved this person. That's your job. You just did your job. Settle down. So we're going to start thumping chests and screaming in here when we get a problem right. Not really. It's just bizarre, Yeah, you can give a little high five now and then. That's good. But it's your job, Just do your job. You can be happy about it, but just settle down. It's your job. Yes.
At 9:59, I'm thumping my chest when I get that WebAssign done.
Okay. Well.
Right on time.
Okay. At least the cameras aren't rolling, right? Okay, let's finish with this problem. Didn't quite get everything that I thought we'd get to, but pretty close. So I guess I can't thump my chest since we didn't quite get everything. I mean, I'm all about being happy, but, just settle down. It's your job. Any suggestions or recommendations? What'd you say?
Skip it.
Skip it? No, that's not a valid recommendation. Just think of anything that we've done today, and I bet you if you come up with something that we've done today, it has a chance of working in this problem.
Change one of them to 1 minus.
Okay? Change one of them to 1 minus sine squared or 1 minus cosine squared. Not to say that we're going to be delighted with the results,
Oh, we're not.
but is it a problem that we have the ability to work?
Yeah.
It is. Okay? So we've got, unfortunately, even powers of sine and cosine, but we now know how to handle that. We'll make these double angle identities, substitutions, and we'll go from there. So it is a workable problem. Can anybody else think of another method that we have used today that might have a chance? Do what, Mandy?
You could switch cosine into 1.
Okay, we could switch cosine squared to 1 minus sine squared. Same basic process. Again, we'd be stuck with even powers of sine this time, right? What else have we done? What type of substitution have we made for that?
Use
And what substitution have we made for that? We just did what for sine squared? 1/2 times what?
1 minus the cosine of 2x.
Right? So we could plug that in for sine squared. Aren't we going to have to do that kind of stuff eventually anyway? When we get here and here? So you might just say, I know I'm going to be stuck with even powers. Let me go ahead and get that out of the way. And for cosine squared,
1 plus cosine.
1 plus cosine 2x. Now, does this potentially have an advantage? It might. The half times the half, we can get that out of the way. It comes out as a fourth. What's the nice thing about these two? We don't have a middle term. Okay, so it might end up being exactly the same amount of work, but at least when we multiply them together, we've got first term squared, which is 1, minus second term squared. Right? And unfortunately, we're going to have to do that process again, right? But aren't we going to have to do that up here anyway? I think this actually gets there a little quicker. Because we're kind of, I guess, technically about a third of the way done when we get here on this problem, and we're just getting started when we get this substitution. So a lot of times you'll have options, and they'll both work, just kind of what you think is the best option. I've got a minute left. Let's see what kind of recommendation. We haven't even talked at all about these. And I think I wrote this down on my sheet today because I think there's a WebAssign problem that has secants and tangents in the integrand. And we'll address this more than just this 1 minute. Is this integrable in the form that it's in? Maybe that's the case. What are the thought processes here? And then we'll stop and we'll start class with this tomorrow. Derivative of tangent. These are the kind of things you need to be thinking about to see if the stuff is in the integrand that needs to be there. What's derivative of tangent?
Secant squared.
Ooh, I see one of those. Okay. What's derivative of secant?
Secant x tangent.
Secant, tangent. That's the bad part. We also see some of those, right? But, how about this? I kind of like that. If we let u equal tangent, this would be tangent cubed, so it's u cubed. Is this together with this du? That's good. We don't need to make any kind of a radical substitution. But these are the two things that will kind of guide us on the secant tangent integrands, and we'll pick up from this point tomorrow. Yeah.
Great math opportunity.
Yeah.